So let's welcome our next talk about Projector Monte Carlo. Let's welcome Joachim. I'm pronouncing correctly.
Joachim Brand. Yeah, thank you very much. My name is Joachim Brand. I'm going to talk about Projector Monte Carlo and exact diagonalization with Rimu.jl. And there's a QR code with materials, both code and slides. All right, so just to make sure that I don't run out of time, I'd like to acknowledge here collaborators. Let me start at the beginning. So the research and also the code is inspired by Ali Alavi down here. So the picture is from a joint group photo during a sabbatical in Stuttgart. So Ali is, pioneered the method. So they're quantum chemists, and they use this as a quantum chemistry code to solve quantum chemistry problems. Now, what inspired me, and so here Elke is my lovely wife. So we thought about together, we want to actually apply this to more general problems that are not quantum chemistry. So quantum particles that can be bosons, fermions with different spins, mixtures. And we started writing our own code. And then later, a number of students and postdocs have contributed. In particular, I would like to point out Ray, Chris, and Mattia. And recently, Mattia has been doing really, really good work on the code. And some of the algorithmic things that I'll be presenting are basically his work. Okay, so we're based in New Zealand, far away. There's a map. We're part of a research center that's actually delocalized across the whole country, and Massey University is here on the outskirts. Our campus of Massey University is on the outskirts of Auckland in the far north. So what do we want to do? We want to solve a number of quantum mechanics related problems. We find, so the first and foremost is to find the ground state and low-lying excited states of a large quantum Hamiltonian. And here the emphasis is on quantum many-body problems, so the Hamiltonian is large. In principle, it's so large that we can't represent it. We can't even represent the eigenstates. So the previous talk, tensor networks is one way of reducing this exponential complexity that we have. So we're going to do it with random numbers. So there are a number of other problems that we're actually also interested in, which is quantum dynamics, finite temperature physics, open quantum systems, and the references here all point to papers that have demonstrated that this can be done with the method, full configuration interaction quantum Monte Carlo, the flavor of Projector quantum Monte Carlo that we're implementing, but they're not available in a single code. There are basically two open source Fortran codes that solve implement this method, but they also have their limitations and are basically geared at quantum chemistry at dealing with problems with electrons. Now, what motivates us, particularly in my research here, is the physics of ultra-cold atoms and molecules. So you can build artificial quantum systems with that. So here's an example of a quantum gas microscope experiment. So there's lasers here manipulating, generating an optical lattice potential. After these atoms have been cooled to nanokelvin temperatures in some vacuum chamber, and then there's a very powerful microscope from the bottom that can resolve single site and single atom what these particles are doing, and their motion or their quantum states are fully quantum mechanical. So every time you photograph it, basically you take a quantum measurement of the position of these particles. So very impressive experimental progress, over the last few decades. Now, so what is Rimu? Name of our package. Rimu is a native tree of New Zealand. It's also on my shirt. Yeah. But yes, we've been using it as an acronym. Sorry if this is a little bit small. I'll read this out. Stands for Random Integrators for Many-Body Quantum Systems. So currently we're mostly implementing this full configuration interaction quantum Monte Carlo flavor of Projector Quantum Monte Carlo. But the idea is we want to be a bit more general and want to do more than that. Currently, what we're doing, what the code can do is interact with quantum many-body models. So we can, for example, do matrix-free exact diagonalization of quantum many-body models if they're specified in our in the interfaces that we've implemented. So we have a suite of quantum of basis states, of Fock states, slated determinants to represent these kinds of problems, and we have an interface for defining many-body Hamiltonians, and I'll show you some code examples later. Predefined examples here are Hubbard models, Hubbard-related lattice models, also transcorrelated Hamiltonians for contact interacting particles, quantum particles, as relevant for ultra-cold atoms. And then some statistical analysis. So why this particular flavor, full configuration interaction quantum Monte Carlo? So it goes back to publications from Alabi's research group in 2009. It's fairly recent, even though the idea of projector quantum Monte Carlo is actually very old. The first paper I found was from 1962. K-loss, Green's function, Monte Carlo, and then diffusion Monte Carlo came about a decade later, and then there are other flavors, auxiliary field and path integral ground state Monte Carlo, all trying to solve the same problem, basically a Hamiltonian that is way too large and you still want to find out what is the ground state energy or what are its properties. Now, what I like about the particular flavor here is that even though it was particularly developed for quantum chemistry problems, it's really just a stochastic extension of exact diagonalization. So you can, anything that you can represent as a large sparse matrix, basically you can throw at this method and it will tell you something about it. Right, so here are a few milestones. I don't need to go through all of it. It's just a few. So from 2009 on, there were some important developments, mostly by other people. Our modest contributions here are, in particular these two papers down here about modifying the algorithm to make it actually a little bit more convenient to control population, and then analysis of a population control bias that I will later show you in action, actually. Right, so starting point is a Fock space basis. So we have a many-body quantum state, psi naught, using physics notation here, and maybe we'll switch to more linear algebra notation later. So there's a coefficient vector, and there are basis states. So these basis states are Fock states. So here's an example of bosonic Fock states, but they could be, bosons, fermions, anything. One problem is, one particular problem that I'll show you examples with is the Bose-Hubbard model. It's represented in this very compact way, but it's basically just a recipe to calculate matrix elements from in this basis. And the matrix elements, they look like this formally, and then eventually you end up at a basis, at a matrix of numbers, but they're indexed now by these Fock states, and the Fock states are represented explicitly in the code. It's very sparse. Here's a sparsity pattern. So now, what do we do to find the ground state? So it's really a generic linear algebra problem, finding the lowest eigenpair of this matrix. So it can be solved with a variant of power iterations, which is applying this operator t, multiplying that repeatedly to some vector, some initial vector, and this transition operator T is essentially, contains minus the Hamiltonian with some time step parameter. There's a scalar parameter S that we call it the shift. It's quite important. It has to be, we adjust it at every time step, because if we don't do this, this would be just exponentially growing or exponentially decaying. So we don't want that. Didn't write out the equation explicitly of how we do that. But if we do that to control the norm, then eventually this becomes a fixed point method, fixed point iterations, and it's easy to see that when this converges, that eventually the coefficient vector will be the exact eigenvector, and the scalar shift will converge to the ground state energy. Okay, so now there's a code example. Let me switch to this Jupyter notebook. So here, let's go through the code a little bit. Already loaded the packages. Rimu is a registered package. So how do we represent Fock states? So we use an occupation number basis. BOSFS stands for bosonic Fock state. This is just two bosons in the first mode, two bosons in the second mode, and so on. So these modes, they can represent, in this case here for Bose-Hubbard model, they will represent lattice positions, or they could be orbitals for chemistry-like problems. They're represented very compactly as bit strings internally. So specifically for these bosons with fixed particle number, we have an encoding that has to be read from right to left now. Two bosons, 0 marks the boundary to the next orbital or the next mode, two bosons in the next one, and then 1 and 1 boson, as you see it here. But we have a number of different ways of representing these efficiently. We also have a shortcut notation here, which we use for printing out, which is quite convenient. Just for an example, we have composite addresses here, so there are two fermion components, so this would be spin 1/2 fermions would be represented this way, again with a convenient shortcut notation. Now we have represented the basis states, so how do we store quantum states? In particular, we want to store them sparsely because we don't want to store all of it. So internally, this works with hash tables, with dictionaries. So this is so that we can, access the value of an address very quickly. Another way to do this would be to keep a sorted list, but that is very expensive if you scale it up. So this is quite convenient. And for addresses that have not been explicitly stored, this just returns 0. So conceptually this is a vector, but of course it's not a vector that it's not a vector in terms of Julia's vector definition. It's not an abstract vector. So now then, we have the quantum states. Now let's move to the Hamiltonians. We've defined an interface for abstract Hamiltonians, and it's fairly simple. So there are these functions, these methods here that you have to implement, and if you want to use that, starting address basically defines the address space. Diagonal element, once you're given a Hamiltonian and an address, you need to be able to compute the diagonal element. Number of off-diagonals is the number of non-zero elements given an address that are in the column of the matrix of the Hamiltonian, and get off-diagonal is to access them. So that is all that is needed to define this Hamiltonian, and then there are a few optional methods that make working with it more convenient. And once you have that, you can do something like vector matrix multiplications So here's an example. How does a Hubbard model in real space look like? It's defined by these equations. And so here we have something that is, this is our predefined method, predefined model. And the nice thing is we can throw it at now address types of bosons or fermions or even composite particles. And whether it's a Bose-Hubbard model or a Fermi-Hubbard model will be decided by which type of address you pass in. And there's various geometries. So let's do this. Let's instantiate a Hamiltonian. This would be a Hubbard real space for a bosonic, the initial state that we defined earlier. So now we have that. We can calculate the diagonal element. Now it's very important, of course, because we'll be doing this, during the Monte Carlo algorithm again and again, that this is really efficient. So, and thanks to Julia's amazing capabilities of just-in-time compilation, this compiles down to very fast code. So you see it takes only a few nanoseconds to calculate the diagonal elements. Off-diagonal elements for this particular model take a little bit longer, 50 nanoseconds or so. But if you implement your own Hamiltonian, it's very important that that is done efficiently. Right, so the particular one that I've instantiated here is small enough that it can be represented as a sparse matrix. So this is implemented just by calling sparse, or can be converted into a matrix here. And now the nice thing is now you can start doing exact diagonalization, and you can just use Julia's linear algebra ecosystem to do linear algebra on it. However, we can also do matrix-free exact diagonalization, which is a very nice feature. And we didn't even have to implement that ourselves, but we're using an external package, Krylovkit. I just found that at some point, that this package exists. It implements the Lanczos algorithm for finding the ground state of a Hamiltonian. It doesn't know anything about our types. It's agnostic, but it doesn't require vectors to be abstract vectors and operators to be operators. It basically works with duck typing. So you could use the functions of Krylovkit directly themselves, or we've implemented here a nice interface inspired by the SciML way of doing things, defining this as an exact diagonalization problem where we just specify an algorithm which is a matrix-free Krylovkit solver, and then we call solve, and it will run the Lanczos algorithm, give us a result, and here we see what the eigenvector looks like. Right, so now let's do quantum Monte Carlo. This was just linear algebra so far, numerical linear algebra. So we instantiate a projector Monte Carlo problem, and you see it prints out with quite a lot of details. This is all the options that I didn't specify, but you can specify them as keyword arguments of specific algorithms that you want to use, for example, or time step details. I'm just using defaults here. So, and that can be solved and should run fairly quickly. Returns a simulation struct. Now we can extract a data frame from it, which gives us a time series. Yeah, we're stepping through, we're doing these iterative applications of the transition operator here. And then we can look at this by plotting the norm, for example. The norm is not held constant, but it's controlled by a parameter, which is called target Walker number. We've set this to 1,000. So there's a transient until the norm gets to where it should be, and then it just fluctuates around it. So if we look at the shift, You remember the shift is the parameter that converges to the exact ground state energy. Again, there's some transient, and then it will fluctuate around the exact ground state energy, which is exactly what it does. Compare it here to the exact energy that we've calculated previously with the Landhaus algorithm. Okay, so that works, but obviously this was a ridiculously small matrix. You wouldn't need quantum Monte Carlo for it. So let's do this with a larger Hilbert space. Here we have 20 bosons in 20 modes. And we instantiate a Hubbard model, Bose-Hubbard model with it. So now how large is this Hamiltonian? How large is the Hilbert space here? It's 7 times 10 to the 10. So that's already something that I wouldn't be able to just do by exact diagonalization on my laptop. Again, we instantiate a Monte Carlo problem, then we solve it, and this also runs very quickly. Again, we plot the norm. Here now we see it fluctuates around this 1,000 value of 1,000 that was given as a target. Also, the shift is very noisy, and for comparison, so it fluctuates, and for comparison, I've given here an estimated number of best value that we know about the ground state energy. You see that it fluctuates a little bit higher. So the important thing, of course, once you have results like that, is to do statistical data analysis on it. I mean, it's fairly simple for the energy. Really, you want to calculate the mean as an estimator, but then you want to know also, how accurate is that. And so this is done with a blocking analysis here that essentially removes correlations, autocorrelations in this time series. And that gives us a value and an error bar here. So this is plotted. In here, you see the value is quite a bit higher, and the error bar is the width of this bar here that we see. Okay, so what has happened? Now we didn't actually get the energy out that we wanted, that we were hoping for. The reason for is that there's a population control bias. It's a statistical bias that comes from the fact that we have such a lot of noise in the way we're doing things. So actually I was a little bit surprised when we first found this, because in the literature people don't mention this very much. But for this type of problem it turns up. So it's something that has to be dealt with. On the other hand, there's a lot of experience on how to deal with it. Okay. Very well, I'll go quickly. So importance sampling is the right way to do it. So this is implemented here very simply with a wrapper of the Hamiltonian. It's a very simple way of doing importance sampling. Now we solve it again. Plot the result. And you see that this is now much closer, has a smaller error bar. But you see also the numerical resources. All of this ran in real time on my laptop, are really small for this really large problem. If we use more walkers and more computer time, we will get more accurate results. Okay, let me quickly switch back here. Right, so the actual stochastic sampling procedure resembles mostly matrix vector multiplication with the additional step that we're stochastically compressing basically vectors twice. Once it is done on this column of the matrix, and once it is done on the final vector. And the stochastic compression removes a lot of the values by keeping the expectation value the same, but reducing the number of elements that we have to store. I don't have much time, so I don't want to go into too much detail on how we parallelize this, but We've worked out a way to parallelize this with threaded operations to avoid memory races. It's fairly efficient. We parallelize with MPI on HPC. This also works quite well. We distribute the vector, all the data actually across the different nodes of HPC and of our high performance supercomputer, and then use MPI in every time step to communicate things. So it took us a while how to figure out how to do this well. And recently, so these are I'm showing you the first benchmarks we've been doing on a really large computer. On Frontier is that. And you see there's a speed up from 20 nodes going to 160 nodes or so, which I guess could be improved. Blue here is really small Walker number. There it's not efficient, and it didn't make sense to distribute it really. But if you have 2 orders of magnitude larger number of Walkers, it starts making sense. Weak scaling benchmark here, we actually went to 1,000 nodes. So this runs now on 1,000 nodes on a large-scale supercomputer, where we increase the number of Walkers for the same problem, which basically increase the number of stored vector elements. So increasing that by 3 orders of magnitude, basically, it slows down by a factor of 6, but it's still actually quite impressive. Right. So we can. So this is just to show that we can do large problems and find here an indicator of the Bose-Hubbard, the Mott-insulated superfluid phase transition in the Bose-Hubbard model. Dimension of Hilbert space here goes up to 10 to the 58. This is really large. Obviously, not all of this is really well needed for the calculation, otherwise it wouldn't work. Okay, I guess I'm at the end. So this is available right now. The rest is future. We're really excited to have collaborators, and I'll leave the funding slide up here while I'm done with the talk. Thank you for your attention.
We still have 1 minute for questions. Any questions? Okay.
Yeah, so I'm just wondering about this interface, this Hamiltonian interface you're coming up with. I mean, your index is essentially quite rich. Like, it has a lot of information about the structure of the system and so on and so forth. But if I'm like in a more traditional quantum chemistry, quantum physics setting, mean field, for example, I often just have a matrix. I just have an index, which is a number, right? Do you provide some support for easily going back? Right? Or is it something I would need to build up, like some mapping from basically
So the index is the Fock state, right?
Yes.
Is the slated determinant.
Yes.
So we just need to know which orbitals are occupied, essentially.
Yes, but I would have to do that manually. So it would be my job to do that mapping.
If you wanted to implement that, you would. Well, in fact, in principle, you can do it any way you like. You could use your own index if you know how to index into that Hamiltonian. It doesn't really matter. This is just the things that are provided.
Okay, so you're not determined on that particular type.
No. It's not necessary to use that interface. But if you have that, and then you have a Hamiltonian that can be written down in second quantization, then you can use our very convenient methods to do that.
I mean, do we have more time? I have a follow-up. Do you have more time? I have a follow-up, but I can also.
But if anyone wants to go to the keynote talk, feel free to go. But technically, this is the.
We are also taking the picture right before the keynote, so if you want to be in the JuliaCon picture.
No, we have to run.
We don't have to.
All right,
Okay, maybe we can do that later, and we go to the picture so that we're in time.
All right. Thanks everyone coming for Quantum Mini. just final reminder that we're going dinner together later after the keynote. Thank you.